Hey everybody, Mr. Armkey back with you for NET-125. Today's going to be a short one. This is going to be a chapter that's all about discussing number systems, but as this only really covers a very limited set of conversions, it's not going to be one of our traditional, 60 to 90 minute lectures. It should probably only take me about half an hour. So let's go ahead and get started. We're going to look at calculations between decimal and binary, as well as decimal to hexadecimal, and how binary and hexadecimal interact directly. So the binary number system relies on the presence or absence of voltage, an off and on, yes or no, true or false value, and it's represented mathematically by a 1 or a 0. These 1 or 0 representations are called bits, and the term bit is a contraction of binary digit. Decimal numbering consists of the digits 0 through 9, so how do we make these line up? Because hosts, servers, and all kinds of other connectivity equipment uses binary addressing to uniquely identify one another. Each address is made up of a 32-bit string in IPv4 divided into 4 sections called octets. Each octet contains 8 bits, which is represented as what we call 1 byte, separated by a dot. For the ease of use by people, this dotted notation is converted to and referred to as dotted decimal. We use what's called binary positional notation. We use what's called a radix or a base in order to indicate the original form of a number system, and then the conversion change by means of what we call numerical position. Positional notation means that a digit represents different values depending on the position it occupies in the sequence. So on the right, we see here the decimal notation system, where if we have a radix of 10, meaning that we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then start over again, but have added a new digit to the left to indicate the increase in rank. That allows us to calculate things formulaically. So if we look at, in this case, the number 1 to a power of 10, we have to indicate a power of 10 to the 0 power. The 0 power, which is the positional index, means anything to the 0 power is 1. On to the left of that, we see 10 to the first power, position 1, means we calculate it as 10. So anything to the first power is itself. 10 to the second power, or 10 squared, based on position 2, gives us a value of 100. Usually with powers of 10, the power to which we are measuring is the number of zeros on the end of the number. So 10 to the 0 power, there's no zeros, so there's only the number 1. 10 to the first, there's 1 0. 10 to the 2, there's 2. 10 to the 3, there's 3. So if I were to say 10 to the 6, that means there's 6 zeros after it, easily divided into groups of 3 to show escalations of the actual unit name. So that would be 1 million. Here we can see this positional value represented in a different way using a conventional name that we've learned from the time we were children. Thousands, hundreds, tens, and ones. You know, the ones place, tens place, probably stuff you learned anywhere from 1st to 3rd grade. Maybe earlier if you were a little bit gifted. The decimal number conversion allows us to calculate these things together. So if we say that we have 1 in the thousands place, 2 in the hundreds place, 3 in the tens, and 4 in the ones, we represent that by the multiplicand of the position value and add them up. So 1,000 plus 2 times 100, or 200, 3 times 10, which is 30, and 4 times 1, which is 4, gives us 1,234. In binary, it's actually a little bit simpler in terms of how we calculate escalating sizes of numbers. The only reason it doesn't make sense to us intrinsically is because it's not what we've been taught from the time we were very young. Also, if you're ever curious as to why we use a decimal counting system, just take a look at your hands. So the radix here is no longer 10, but 2. The position in the number, we now have an 8-bit length, and because computers have to start from a concept of 0, we have a representation that has to start with the 0 position. So we have 2 to the 7th as being our 8th position, 2 to the 6th is our 7th, etc. So this means that the maximum representable value in this case should be represented by 2 to the 8, which is 256, and you'll find that that clocks. 256 individual numbers can be represented by an 8-digit binary value. So if it's 8 digits long, in binary it's 2 to the 8, which means that it can go from 0, has to start with 0, to 255. If you add 128, 64, 32, 16, 8, 4, 2, and 1, all of the various powers that are representable by those individual positions, we would then get 255. Let's look at an example of that now. If we have the binary number 11000000, we can calculate based on our positional values. So 128, or 2 to the 7th, is in position 1, and the binary number 1 is there, which means yes, 128 is present as part of our value. 1 is present under the 64 position as well, so that indicates that 64 is part of our number. The way that it was described to me when I was first learning this was that binary is more evidently than decimal a gestalt, meaning it's an assemblage of its parts. We have a 1's place, a 2's place, a 4's place, an 8's place, etc. So if we add 128 and 64, we're keeping it real simple. 128 plus 60 would be 190, or 188, excuse me. So 6 plus 2, because we're doing it in a columnar addition. And then 8 plus 4 is 12, so we bump up the 10's place to 190, and we leave the 2 remainder at the end. So that gives us 192. The reason that I'm glad they use this as their example as well from the text is that this is representative of something that would be an appropriate subnet mask. We can see that we have a string of 1s that is uninterrupted, and then we have our dividing line between the 64 and 32 position to where it becomes a chain of uninterrupted zeros. So in this case, if we were to see a 255.255.255.192 subnet mask, which we'll talk about later in the semester when we get into subnetting, individual subnetting, what's called VLSM, we would see that this is a /26 subnet mask. So this is a type of entry that we'll see again and again and again. So let's convert now from a binary representation, an IPv4 address, if you will, into decimal. Now this table does get a little bit complex, so let's just take it one step at a time. We're going to take our 4 dotted decimal numbers, our binary entries, and put them into a 3-row group and do 4 separate groups, one for each octet. So rows 1 through 3 will be 11000000. Row 4 through 6 will be 10101000. Rows 7 through 9 will be 00001011. And rows 10 through 12 will be 00001010. And it really does become a game of fill in the blanks after that point. We have, from our previous example, 11000000 being 192, but we'll go through the math again. 1 times 128 plus 1 times 64 gives us 192. In our second set, we have 10101000, which gives us 1 times 128 plus 0 times 64 plus 1 times 32 plus 0 times 16 plus 1 times 8. Once you reach the end of the string, as far as represented by the 1s, and it's all zeros heading on, you don't have to continue. So we'll just say 128 plus 32 plus 8. Now, I personally, just to make it easier mathematically, because these groups of numbers tend to line up pretty comfortably, and you see that it's a repeating pattern of 2, 4, 8, 6 as it goes through, as your ending numbers, I like to add them together in ways that make 10, because again, we're trying to make decimal sense. It's what our brains are trained to do. So I will add the 32 and the 8 together. That gives me 40. So now I only have to worry about adding it one place. 128 plus 40 becomes 168. That gives us our second dotted decimal octet. Now we're heading towards the right-hand side of the binary numbers here. We're going to ignore those leading zeros and go straight to 1011. So that means 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. So 8 plus 2 plus 1 is the same thing as saying 10 plus 1, or 11. That's our third octet. 1010 is the same thing as saying 8 plus 2, one less than our previous entry, which gives us 10. So that means that if we convert the binary address that we saw at the top, we now have a dotted decimal address of 192.168.11.10. So when we're doing this conversion, we want to take a look at our most significant bit. Is the decimal number of the octet n, n being our decimal position, greater than or equal to 128? So we're doing a comparison here. This is a little bit easier for people who like to do subtractive math. So at this point, we go ahead and record if this number is here, let's go ahead and say yes or no, and then we'll go ahead and take the remainder and go to the next position to the right. And we will continue this process until we run out of remainder. So let's take a look. Let's take the decimal number 168. Now I can hear some of you getting ahead of me. 168 is 128 plus 40. We've already converted this one. But let's go ahead and go through the process. 168 is greater than or equal 128, so that's a yes. Binary in this case is representing yes as this being a component of the composite number. So we're going to put a 1 in position 1 and subtract. 168 minus 128 is 40. Is 40 greater than or equal to 64? No. So we're going to put a 0 and move on to the next, carrying that remainder forward. Is 40 greater than or equal to 32? Yes. So we're going to go ahead and put in a 1 in position 3, and now we're going to subtract 32 and take our new remainder, which is 8. Is 8 greater than or equal to 16? No. So we'll put our 0 and move on. Is 8 greater than or equal to 8? Yes, it's equal. So we're going to go ahead and put in 1 in the P5, the position 5, and subtract 8. Now that we've got a 0, we have no remainder, so the rest of the string becomes zeros. So decimal 168, as we saw from our previous slide, is verified as being 10101000. Decimal counting is good for humans, so we do like to have the representable decimal conversion. But computers and routers only understand binary, so it's important that we know how to communicate with these two numbering systems. And the good news is, the more comfortable you get with these two, the easier hex will become, which for a lot of people is very confusing at first because you're, again, not dividing by a simple number that's easy to count by, either counting on your hands or by counting 1 or 2, yes or no, off or on, which is a little bit simpler once you get comfortable with it. Hex is based on hexa, from the Greek meaning 6, and deci meaning 10, so that's 10 plus 6, 16, is a number system that includes letters. And I've heard, I can't tell you how many stand-up comedians include the idea that, I was fine with math until they started including the alphabet. And that's all well and good, but it's just symbolic. That's what I want you to think of. This is just symbolic usage of letters. So hexadecimal, instead of using the number 10, we'll use the letter A. 11 becomes B, 12 becomes C, and so on. This is just for cleanliness' sake. It's easier to write it as a single character, so that's why we do it. Hexadecimal is used to represent IPv6 addresses and what we call MAC addresses, media access control addresses. Now, if you take a look at the binary representation in the middle column, you see that it's a standard ascending count. So 0 is 0, 1 is 1, 1 0 is 2, going on until we have all ones. Now this is not by accident. This means that we are able to represent things in these half groups of binary counts called nibbles. Yes, computer scientists like to have dad jokes too. Half of a byte is a nibble. So we can see here that we group these hexadecimal digits into what are called hextets. 4 hexadecimals in a group. Each of those hexadecimal hextets means that we have 4 bits and 4 characters, so that's 16 each. So that's 16 bits making up each hextet to represent. So we can see here from the graphic, we have X separated by colons. Well, the X represents each hextet, which can be anywhere from 0 to 4 Fs. which becomes anywhere from all zeros to all ones, 16 bits long. That's why IPv6 addresses are 4 times longer, because we use the hexadecimal counting systems. Now, a 32 character address, not 32 bits, but just 32 characters, can represent the same value on a page, but be 4 times the level of complexity. It's actually to the power of 4, not 4 times. So let's go ahead and take a look at how to convert a decimal number into hexadecimal. We have to have an intermediary, and that intermediary, of course, is binary, which is why we did it first. So let's go ahead and convert the decimal number into an 8-bit binary string. 168 we've seen before, and that's 128 plus 32 plus 8. So that gives us 10, 10, 10, 00. 10, 10, 10, 00 in 2 groups of 4 sequentially becomes 1010 and 1000. These nibbles can be converted to their equivalent hexadecimal digit based on the table or based on the mathematical equivalence of the binary value. So 1010 is the same thing as saying 8 plus 2, which is 10. And remember, in hex, we start with the letter A after the number 9. So A is 10. And then 1000 is the same thing as saying 8 in decimal. And from 0 to 9, decimal and hex are equivalent. So now we put those 2 nibbles back together after they've been converted, and we usually apply the prefix 0x. 0x helps us to indicate, depending on what we're looking at, especially for writing memory addresses, which also use hex for shorthand, that we're talking about a hexadecimal number. Because if you write the number 11 in hex, it's 1, 1, so that would be 2 places giving you a different value as opposed to the number 11 or the number 1, 1 in binary. 1, 1 in binary would be 3, and then in hex you'd be looking at I believe 17. I'm sorry, 16. I got ahead of myself. 16. So the number 11, the number 16, and the number 3, depending on what your number system is going to be equivalent. Not a type of confusion you would like to introduce. So for hexadecimal to decimal conversions, let's go ahead and take a look at our process. It's essentially the same thing we did for converting decimal to hex, but it's reversed. Of course, we're going to take the hex number, split it into 2 4-bit binary strings, and then create the grouping from the rightmost position. So if we take D2, D is equivalent to 13. So A is 10, B is 11, C is 12, D is 13. And then we have 2, which is, of course, number 2, and convert it. So how do we convert 13 based on powers of 2? Well, 8 plus 4 is 12, and then add 1 more. So 1, 1, 0, 1. And then for 2, we just need 2, so that's 1, 0. We go ahead and put it together, 1, 1, 0, 1, 0, 0, 1, 0, and then we convert that. So this is 128 plus 64 plus 16, because we're skipping 32, we're skipping 8, we're skipping 4, and we're adding 2. And then we've got the 0 at the end. So 128 plus 2 is 130, and then 64 plus 16 is 80. So if we have 130 plus 80, that's 180 plus 30, or 210. So that's how we get 210 in decimal. Again, it's a little bit easier if you're doing it on paper as you follow along. You'll get a little bit better about doing it in your head the more practice you give. I guess that's the one thing I'll emphasize about this chapter while we're discussing it, is that this is a chapter that is not necessarily sitting down and absorbing the information by reading. It's really refining your not really muscle memory, but your immediate memory by doing. So that is it for Chapter 5, only 17 slides. Hopefully you learned something. If this is something that you already knew, hopefully this was a refresher. Maybe it gave you a different method by which you will be able to refine your skills. And other than that, if you have any concerns, as always, you can text me or call me at my Google Voice number, 910-239-7814. Or you can email me at jearmke063@cfcc.edu. Thank you so much for your time and attention, and I'll see you next class.